Okay, let's start. Welcome everyone to our last seminar of the year. While we had to adapt a lot this semester for remote seminars, I'm very happy with the outcome and your participation. But I'd like to thank everyone that devoted their time to get this organized, especially Nicole with the Astro IT team, the moderators of the breakout rooms, and the UFRGS social media team for the art cards and the organized posts on Twitter, Facebook, and now also Instagram. Great job, guys. Now I'd like to introduce our speaker today, Marta Reina-Campos, who obtained her PhD at the University of Heidelberg a couple of months ago, where she worked with Diederik Krause. Before that, she completed her bachelor studies at the University of Barcelona and a master at the University of Barcelona with a semester in Leiden as an Erasmus student. Marta is about to move to Canada, where she's starting a postdoc position as a CITA National Fellow at the McMaster University. Thank you so much, Marta, for accepting our invitation. You may start when you're ready.
Thanks, Anna, so much for the kind introduction and also for inviting me to speak here today. So as she said, my name is Marta, and today I would like to talk about how we can try and model massive stellar clusters from when they are born until and their entire evolution over a Hubble time of cosmic history. And we will be able to run simulations like the one that we're seeing in the background here. So before starting and becoming too technical, let me go into describing what do we understand as globular clusters. Here in this slide, I'm showing two objects that you can see, and these are two typical globular clusters that we see in our own galaxy. And these objects are massive stellar clusters that are gravitationally bound and tend to have not only extremely massive, extremely large masses, so extremely large number of stars, as you can see from this image, but they also tend to be relatively old and relatively metal poor. And I like this quote from the second catalog by Herschel because it's one of the first definitions that I have found from an observer looking into the universe, being surprised by these type of objects and starting to describe their physical properties. And what Herschel describes is that stellar clusters seem to be or seem to present a large number of spots of equal luster, which we know are stars that are scattered over a circular space. And this is what makes globular clusters quite peculiar as well. It's not just that they have very large masses in a reduced space, it's also that these stars have this spherical shape. And this is where the term globular comes from. So because these objects have these quite interesting properties, we would like to understand where these objects form. And we would like to understand whether the conditions that, what were the conditions that led to their formation. But before going there, we can take a step forward, and rather than focusing on the objects themselves, we can try and explore where these objects are sitting. And what you're seeing now is how Gaia, how the second release of Gaia DR2 sees the Milky Way. So this is a stellar density map of our own galaxy. And what you're seeing is that the galaxy is oriented in the image such that the plane of the galaxy is this horizontal plane here. And all of the dark clouds that you're seeing are dust clouds that are extincting the stars that are on the other side. And that's why they appear dark, because we cannot see whatever is on the other side. What is really remarkable from this figure is not just that you can see some satellite galaxies, such as Sagittarius here, and the large and the small Magellanic clouds, but we see some very, very bright spots in this image. And we can now take a step further and annotate the image, and we see that some of these very bright spots correspond to globular clusters. So the objects that I was mentioning earlier, these extremely massive gravitationally bound stellar clusters that tend to be relatively old and relatively metal poor, are scattered all over the place in our galaxy. So there doesn't seem to be a particular place where we would expect them to see. Some of them are in the outskirts, but there seems to be also a bunch of them that are sitting in the galactic plane. So this just adds a bit more mystery into these type of objects. So we can take a step further, and rather than just focusing on the very massive end of this stellar cluster population, we can try and take a look at what do gravitationally bound stellar clusters look like in the Milky Way as well as in the Magellanic Clouds. And what I'm showing here is one of the figures by a recent review by Mark Krumholz and collaborators, and I really like this figure because in these 8 panels, it shows the wide variety of properties that these stellar clusters show. So going from the top left panel, this one here, down to this panel here, you can see a collection of stellar clusters in the Milky Way as well as in the Large Magellanic Clouds, and they are ordered based on their ages. And as you can see, because their ages are listed in the top part of the panels, we have a wide variety of ages represented in the stellar cluster population in our galaxy and their satellites. So some of the stellar clusters are currently star forming, and some of them are extremely old. So it says here more than 10 gigayears ago, but the median age is more like 12 gigayears or something like that. And not only we see this wide variety of ages in the stellar cluster population, but actually these objects show a wide range in their masses. So some of these objects are merely 100 solar masses, whereas some others can be 10 to the 5, 10 to the 6 solar masses. And they also show a range in their metallicities as well as in their chemical abundances. So the fact that we see that gravitationally bound stellar clusters in these 3 different galaxies shows such a wide range of properties leads to the suggestion that maybe there is a unique physical mechanism that drives the formation of these objects, and that this physical mechanism might depend on the local gas conditions from which these objects form. And so it is the formation of these objects and their evolution over cosmic time what sets the properties that we are currently seeing today. And within this picture, we would expect that the massive globular clusters or the massive clusters that we identify as globular clusters would just represent the extreme metal poor, massive and old end of this distribution. What is very interesting of this suggestion is that it predicts that we should be observing massive cluster formation in the local universe if the gas conditions are adequate. And if we look around in the local universe, we actually see that there are some globular cluster-like objects that are forming wherever there is high gas pressure and high rates of star formation in interacting dwarf galaxies. And we've been calling these objects young massive clusters. These superstar clusters or bluish cluster complexes were first observed using ground-based telescopes, but over the past 20 to 30 years, the Hubble Space Telescope has been doing a lot of observations of these interesting interacting systems and has been finding many young stellar cluster populations. And the first place where a group of researchers used the HST to observe was the Antennae galaxies. So as you can see from this very extremely beautiful image, all of these blue compact regions are extreme star-forming regions, and many of them host these young massive clusters that we would expect from the suggestion that stellar clusters might form via a unique physical mechanism. And we see this not only in the Antennae galaxies, but this is also a really nice figure by a recent paper by Angela Damo et al. And et al. From this year. And you can see the galaxy in the gray color bar, and all the young stellar clusters are represented by these colored dots, and their masses are indicated by the color bar. So these lead some support to the idea that stellar clusters might form through a similar physical mechanism over cosmic time. But in order to see whether this is actually true or not, we have to compare the properties, or we should compare the properties of these young massive clusters with the properties that we see for globulars. So what I'm showing here in the first row are 3 different examples of young massive clusters observed in different galactic environments. And then here in the bottom, we have 3 different examples of globular clusters. And what it is quite interesting when we compare the properties of these 2 subsets of stellar clusters is that in terms of their masses, they're quite similar. In terms of their sizes, they're also quite similar. Both types of stellar clusters trace the stellar component of their galaxy, and they mostly differ in 2 things. The first one is that young massive clusters are currently forming, because that's per definition. And the second one is the environment in which these clusters are sitting, because young massive clusters are or tend to be still embedded in their natal gas environment. So they're in these extreme gas regions, whereas globular clusters are observed in the outskirts of galaxies as well as in the galactic planes. So this leads even more support to the suggestion that we can understand stellar clusters as having formed through a unique physical mechanism over cosmic time, which would imply that then we can understand globular clusters as these products of regular cluster formation that has been happening over time, and the objects that we observe to be globular clusters today are the ones that have managed to survive until our present day and to us. So this is a hypothesis for how globular cluster formation and evolution has proceeded. And in order to see whether this is what describes reality or not, we need a description, we need a model or way of modeling this. And this is an analytical end-to-end model that was put forward in 2015 that suggests that young massive cluster formation would happen in the extremely gas-rich environment of high redshift galaxies. And because these galaxies are so gas-rich, these clusters would undergo a lot of tidal interactions with their surrounding environment that would would imply that they would be losing mass very rapidly. And it would not be until the galaxy would undergo a merger that the cluster population would be able to migrate outwards towards the outskirts of the galaxy. And because the outskirts of the galaxy have less gas, it would be more likely for the clusters to survive and to become the globular cluster populations that we are seeing nowadays. And what this model is telling us is that if we want to understand how stellar cluster populations, even just the massive ones, have formed and have evolved over cosmic history, we also have to account for the evolution of their galactic environment and their overall cosmic environment. So we have to take into account cosmic evolution. And this is actually quite a challenge. So, and this is going to be the goal of my talk, is to discuss how can we model the co-formation and evolution of stellar clusters and their host galaxies. This problem presents 2 big challenges. The first one is that we have to keep in mind the scales that we're talking about. What I'm showing here is an image of the Andromeda Galaxy, or M31. Just some fun facts, and the Andromeda Galaxy has a diameter of about 67 kiloparsecs, and its halo mass is of the order of 10 to the 12 solar masses, with its stellar mass being of the order of 10 to the 11 solar masses. Now, I'm showing here, in contrast, the brightest globular cluster in the local group, which is called M31G1. And this cluster has a mass of 10 to the 7 solar masses, which is about 2 orders of magnitude more massive than the typical globular cluster in the Milky Way. And its half mass radius, it's about 6 parsecs. So half of the mass, so half of these 10 to the 7 solar masses is enclosed within only 6 parsecs. And despite these very large masses, and what this means is that the first challenge that we will have to overcome is the fact that we're working with an extremely large range of masses and spatial scales. And this becomes even clearer if I now just let M31G1 go where it belongs in the galaxy. And as you can see, in terms of brightness, even though this object is a 10 to the 7 solar mass cluster, is nothing compared to the galaxy. So this is going to add some challenge to how we add the stellar clusters in the simulations. The second challenge that we're going to have to overcome is the fact that we want to model how stellar clusters are forming and how they're evolving over cosmic time. So we have to be able to describe how the galactic environment and how the gas conditions are from those extreme gas conditions in which massive stellar clusters form down to the more quieter type of galaxies that we see in the local universe, such as here in Antennae. So we will need a complete description for galaxy formation and evolution. So the first thing that we need to model the co-formation and evolution of stellar clusters and their host galaxy, it is a realistic cosmological hydrodynamical description of galaxy formation and evolution. And there are many groups currently or that have been working on this over the past 20, 30, 40 years. And each of these groups differs slightly on how they decide to treat how the gas cools, or how the gas is turned into stars, or how the stars produce feedback, on whether they include black holes and AGN feedback in their simulations, or whether they include magnetic fields, or even which type of numerical scheme they use for solving the equations of hydrodynamics, or the way that they calculate the gravitational forces. So there's a wide variety of models, and there's a large number of groups working on this. And overall, the efforts seem to be divided on two fronts. So some of the groups are focused on the evolution of cosmological periodic volumes, where they take a chunk of the universe of a certain size and they evolve it with time. And some other groups are focused on studying the evolutions of particular regions within these volumes, so that they can focus around halos that have a given mass. And this is interesting, for example, if one is interested in studying only Milky Way-mass galaxies. Whatever the approach, these groups have some limitations in their studies, and it's the fact that in these simulations, what they generally call a star, it's actually a stellar population, because the typical mass and spatial resolution that these studies have is between 1,000 to 10 to the 6 solar masses for the stellar particles. So there's no way that that can correspond to one star as we see them in the local universe. And in terms of the spatial resolutions, some groups can go down to the parsec scale, whereas the more typical size is of the order of a few hundred parsecs. So these would help us with the description of the galactic environment, of the cosmic environment and how it evolves with time. But now we need to add the stellar cluster populations on top of this description of the galactic environment. So the first thing that we can do is forget about the galactic environment. How would we simulate the formation of stellar clusters? And what many groups do is take a gas cloud and let it collapse over time. And I'm just showing here 3 different examples from 3 different groups, but there's many work being done in this aspect. The interesting thing of these simulations is that now each data point or each star is actually one star as we would identify them in the universe. However, as you can see, the mass and the spatial resolution that these simulations can achieve is orders of magnitude away to what we can achieve in galactic scale simulations. So we have to do something different. So what some groups are doing is to consider that each of the stellar particles can be either one star or a small low mass stellar population, or even they consider that each star can be a sync particle, and this sync particle will accrete gas from the surrounding and might become a stellar cluster. What these simulations or what these groups are doing is pushing the mass resolution of their simulations, trying to go to higher and higher resolution. And this is extremely interesting because they're capable of studying the self-consistent formation of stellar clusters in galactic environments. However, it also has a very strong caveat, and it is that these high mass and spatial resolutions implies that these simulations have a huge computational cost, and which also means that they cannot run that many simulations, so they're going to have a low statistical power. There's another approach that we can take, which is to consider that each stellar particle in the simulation it's going to be describing a subgrid stellar cluster population and some field stars. So what we do in the simulations is that the gas particle will have a mass of about 10 to the 5 solar masses, and then it will turn into a star or a stellar particle in the simulations. And what we say is that within this stellar particle, a fraction of its mass is going to correspond to a stellar cluster population, and the other fraction of the mass is going to correspond to a field stellar population. These stellar clusters and these stars will operate under the hood of the stellar particle in the simulations, and will not interact with anything else. It's something that we do under the stellar particle, and that's why we call it subgrid. And this is the approach that we decided to take. So the E-MOSAICS project combines a subgrid description for cluster formation and evolution with the Eagle galaxy formation model. And combining these two models has been extremely fruitful at exploring from the largest scale structure down to one node from the cosmic web, the galaxy within this node, and the stellar cluster population within this galaxy. Within this project, we currently have a complete volume-limited sample of 25 cosmological zoom-ins of present-day Milky Way-mass galaxies, and we've also run a periodic volume that has 34 megaparsecs on the site, and we've run it down to redshift 0. So with these simulations, we can study not only the stellar cluster populations for Milky Way-mass galaxies, which is interesting because our galaxy is where we have more information about clusters, but we can also explore the stellar cluster populations as a function of the halo mass of their galaxy. And so we can look at clusters of galaxies and the clusters that they contain. So before getting into the details, I just want to show you what a movie of one of our simulations looks like. What you're looking at here is one of our present-day Milky Way-mass galaxies, with the gray color bar being the gas density and the color dots corresponding to the stellar clusters. And I will now go into a bit of detail into how exactly we are forming and we're evolving these stellar cluster populations. But what I wanted you to see is that by combining this galactic environment and this subgrid description for stellar clusters, we can study how stellar cluster populations are forming and assembling over cosmic time at the same time that this galactic environment is forming and assembling. So what do we need to model star clusters over Hubble time? As I said already, we need a description for the galactic environment and how the gas cools down and it forms stars and the stars do feedback. And for that, we use the Eagle galaxy formation model, which is a suite of cosmological hydrodynamical galaxy formation simulations. And something to consider about these simulations is that they model a single phase medium, which means that they do not model the cold phase of the ISM. This galaxy formation model tune its feedback to reproduce some galaxy properties, but it reproduces many other observed properties of the evolved galaxy population, such as the Hubble sequence, as you can see in this image here. Regarding how we form these subgrid stellar cluster populations, we use two different physical parameters. The first one is a description of which fraction of the stellar particle mass goes into forming these bound stellar clusters. Should we keep this fraction constant? Should we let it evolve with the environment? What we decided to do is to use an environmentally dependent model that was developed in 2012 and is represented in this figure by the blue line. So in this figure, you can see this fraction, which we generally refer to as the cluster formation efficiency, as a function of the star formation rate surface density. And all the other data points correspond to observations. So as you can see, the model that we decided to use reproduces quite well the trends that we see in young stellar cluster populations in the local universe. When we put this model in the simulations and we let them evolve with time, we can look at the young stellar cluster populations and what is the cluster, and we can calculate what is the cluster formation efficiency that they form with, and we see that they actually reproduce the observed values in the local universe. So this is giving us some support, some credit that this model does a good job at reproducing what we see in the local universe. Additionally, we can also look at how this quantity evolves with time. And here I'm showing the cluster formation efficiency as a function of redshift. And as you can see, this quantity steeply decreases towards lower redshift because the environmental model that we're using is proportional to the gas pressure. So higher gas pressure environments will form more mass into bound clusters, and higher redshift environments tend to have higher gas pressures than lower redshift environments. The second physical ingredient that we use to describe our subgrid stellar cluster populations is what is the initial mass distribution that these subgrid stellar clusters should have. We know from observations, and it is represented here, that the mass function that young stellar clusters populations show is or tends to be well described by what we call a Schechter function. So that is a power law term with a slope of -2 and a certain exponential cutoff. And this exponential cutoff has been observed to change with the galactic environment. And in particular, it seems to correlate with the star formation rate surface density. So the first project that I worked on was on deriving an analytical model where I considered a galaxy in hydrostatic equilibrium that was differentially rotating, and I studied what was the maximum mass that could collapse under centrifugal forces when we also took into account the effect of stellar feedback. Because as the Tumber region within this galaxy is collapsing, there can be star formation in this region, and so the energy injected as a stellar feedback from these newborn stars can stop the gravitational collapse of the region. And so we realized that we needed to consider this interplay between gravity and stellar feedback to reproduce some trends that we were seeing in the local universe. And so when we put this model in the simulations, we let the simulations evolve to redshift 0, and we looked at what the young stellar cluster populations masses look like. We fit a Schechter function, which is represented here by the colored dots, and we compare them to the observations, which correspond to these blue squares and these other colored dot joined by the black line. And what we saw is that this model, or the evolution of this model in the simulation, actually reproduces not just the trend, but also the scatter that we see in observations. So again, this gives us more support that the models that we're using do a good job at reproducing cluster populations or young cluster populations in the local universe. Again, we can look at the evolution of this quantity with redshift, and we see that it steeply decreases. And the reason for this is that, again, higher redshift environments have higher gas pressures, and higher gas pressure environments are going to be able to form more massive clusters. So we see globular clusters to be massive because they form in high gas pressure environments, and these high gas pressure environments were more prevalent at higher redshift. And so this is why globular clusters also tend to be old and metal poor. So these are the details regarding how we form the subgrid stellar cluster populations. And now, how do we evolve them? In the E-MOSAIC simulations, this means that how do we consider how their mass evolves over time? So in particular, we consider 4 different disruption mechanisms. The first one, which is dominant, is tidal shocks with passing giant molecular clouds, as you can see in the video that is playing here on the left. These tidal interactions inject energy into the stars of the clusters, and so the stars become unbound and leave the cluster. The other environmental mechanism for their disruption that we consider is two-body relaxation in a tidal field. As you can see in the video here, are just interactions between 2 stars, and one injects energy into the other, and that expels it. We also consider the effects of stellar evolution, and we also apply dynamical friction, but we have to do that in post-processing. And just to give you a brief idea of what can happen to the stellar clusters in our simulations, I'm showing here the evolution of the tidal heating as a function of the loopback time for 3 different clusters, so for 3 different cases of clusters. The yellow line represents a stellar cluster that was born in an extremely gas-rich environment, and it underwent a lot of tidal shocking, and then it just quickly disrupted. The red line corresponds to a stellar cluster that was born in a much less gas-rich environment. It underwent many less tidal shocks, and so that's why it managed to survive until the present day. And so the purple line is the intermediate case. This is a cluster that was born also in an extremely gas-rich environment. it underwent a lot of tidal shocking, but at some point its galaxy had a galaxy merger. And so this cluster could leave the extremely gas-rich environments in which it was sitting and move to the outskirts of the galaxy. And this is what it allowed its survival to the present day. So when we put all of the models together, we go back to the movie that I just showed you, where again, we have the gray color bar showing the gas density and the color dots corresponding to the stellar cluster populations that we form and evolve self-consistently over cosmic time. And as I said, what these simulations allows us to do is to study how the stellar cluster populations are forming and assembling at the same time as their host galaxies. And this is extremely interesting. But now there are two questions that we can ask ourselves. The first one is, all of the models that we have put in seem to be doing a good job. But do these evolved stellar cluster populations actually resemble the evolved populations that we see in the local universe? And the second question that we can ask ourselves is whether we can use the redshift zero properties of these evolved stellar cluster populations to understand what was the galactic environment in which these clusters formed. I'm not going to touch the second question, but I'd be really happy to answer questions about it. So what we did in the E-MOSAICS project was we first decided to look at the massive end of this stellar cluster population. And what I'm showing here in these three different panels is the high mass end of the evolved mass distribution, the metallicity distribution, and the spatial distribution. Our simulations are always described by the gray lines, and the Milky Way corresponds to the thick black line. And what we see is that if we only focus our study in clusters that are more massive than 10 to the 5 solar masses, we do a good job at reproducing the mass distribution. We do a fairly good job at reproducing the metallicity distribution, and they're also sitting where we would expect. And we've not only explored these three different quantities, but actually in this range of papers, we've been looking at many, many other ones. So if you're interested, please go take a look. And what this is telling us is that this is providing more support to the idea that globular clusters are the products of regular cluster formation at high redshift that has managed to survive to the present day. However, we saw that the E-MOSAICS simulations had an issue when we extended our analysis towards lower mass clusters. And what you're seeing here is the mass function of stellar clusters divided by the the gas pressure of the environment from which these objects form. And as you can see, there's a moment in which the stellar clusters no longer reproduce the observed mass function in the Milky Way. What we saw is that in the E-MOSAICS simulations, disruption is too slow for those clusters that spend more time orbiting in the gas-rich region of their galaxies. So this affects especially the young, metal-rich, and low-mass clusters. And the reason for this is that the Eagle galaxy formation model does not resolve the cold phase of the interstellar medium, which is critical for modeling the environmental dependence of how these massive stellar clusters form and evolve, because we know that they form in extremely high gas pressure, high density environments, and it is in these extremely gas-rich environments where there are most of the dense structure that will drive their disruption via tidal shocking. So what I've been working on during my PhD has been to incorporate this multi-phase nature of the interstellar medium in a new suite of galaxy formation simulations that also describe stellar clusters using this subgrid approach. So if we go back to this idea of what do we need to model star clusters over a Hubble time, one of the major uncertainties in galaxy formation models are what are the timescales related to star formation and stellar feedback. And so we've been using ALMA observations to derive these timescales, and we've been using this empirical input to motivate empirically motivated description for how star formation and stellar feedback should proceed is observed to proceed. And I've been working on improving the description for the subgrid stellar cluster populations. So we're calling this suite of simulations EMP-Pathfinder, and this is the first step towards this empirically motivated description of the physics of star formation and stellar feedback. And we've been implementing this within the hydrodynamical code moving mesh repo. So what does this mean exactly? It means that we are allowing the gas to cool. In terms of how the gas is cooling, we're using a non-equilibrium chemistry network from the Grackle library that considers the evolution of 6 different primordial species. And as you can see in the phase diagram here, so this is the temperature as a function of density, the gas in our simulations cools down to 30 Kelvin. And we are only forming stars from this cold and dense region of the phase diagram, as you can see from this record of the stars here. We decided to explore how star formation should proceed, and so we are considering 2 different recipes. Some of our runs consider a constant star formation efficiency per freefall time, and another subset of our runs considers that the turbulence of the gas can suppress star formation. And this is going to have, or we expect that this is going to have a very strong impact on how star formation proceeds and what is the morphology of these galaxies after Hubble time of evolution. In terms of the stellar feedback, we're modeling the mass, metals, energy, and momentum injection from AGB winds, supernovae of type 2 and supernovae of type 1a, and we calculate all of these ejected quantities such that it corresponds to the evolution of a fully sampled Chavry IMF, which we calculate using the SLAC library. And I would like to note that this is still not empirically motivated yet, and that's why we added the Pathfinder. Additionally, we're also keeping track of the evolution of 30 different elements and their isotopes. So these are 101 different elements that we are keeping track of as these galaxies are evolving, as the star formation and stellar feedback proceeds. And this means that we will be able to do predictions for studies of galactic archaeology that will be looking at detailed chemical abundances for the stellar component as well as for the stellar clusters. And lastly, about the stellar cluster populations, our goal, or my goal during my PhD, has been to study the stellar cluster formation and evolution in a cold and dense cosmological environment. So relative to the models that I just explained for E-MOSAICS, we're still using the same description of the cluster formation efficiency. So what fraction of the stellar particle mass is used to form the subgrid stellar cluster population, but I have updated which formulations we use for the initial mass distributions of stellar clusters. I have also included a description for the initial size of the clusters to be environmentally dependent, and I've updated how tidal shocks affect the mass evolution of stellar clusters, and we also have a description for how the size of these clusters changes with cosmic time. Each of the galaxies that we run can run several of these models so that we can reduce the influence of the baryonic physics on the clusters. And EMP-Pathfinder is going to consist of 10 Milky Way-mass cosmological zooming simulations that are run at a baryonic mass of 2 × 10⁵ solar masses, and each of them will include 10 cluster populations. So just briefly before finishing, I would just like to show you some results from these simulations. These correspond to simulated stellar cluster populations in emerging galaxy system about 9 gigayears ago. And each of these panels corresponds to a different configuration of the stellar cluster population. So if we compare our fiducial model with a description where we've only changed the initial mass distribution, we see that some clusters have larger masses than in our fiducial model. If we now change how shocks affect the mass evolution of stellar clusters, we see that they tend to be lower masses. If we now combine and we change both the initial mass distribution and the shock disruption, we see that they seem to be somewhat lower masses, and there are also some blue clusters here, so some larger masses. If we now let the initial size to be environmentally dependent, there's a huge and very drastic difference relative to the fiducial model, as we see that there are many clusters, and the large majority have very low masses. And this becomes even more drastic if we also let the size evolve with time. So by using all of these models, we can compare to observations of stellar clusters in major galaxy systems, and we can try and pinpoint which of all of these models actually does a better job at reproducing the stellar cluster populations that we see in the local universe. So just summarizing, I hope I've managed to explain that modeling stellar clusters in a cosmological environment, it's quite a challenging problem because it requires a self-consistent description of many different physical processes over a wide range of scales. And I've introduced the E-MOSAICS project, which reproduces the cluster populations that we observe at the present day, which implies that globular clusters could be the products of regular cluster formation at high redshift, and that they would have high masses because they form in high gas pressure environments, and they would have all ages and low metallicities because these high gas pressure environments were more prevalent at high redshift. And lastly, I've introduced the EMP-Pathfinder, which is this first step towards an empirically motivated description for the physics related to star formation and stellar feedback, and that is going to start producing more results soon. So stay tuned for that, and thank you so much for inviting me here today.
Thank you very much, Marta, for your excellent talk. For the people following the talk on YouTube, thank you for joining us. If you have any questions, please post them in the YouTube channel and our speaker will answer them later. We shall have the new series of seminars starting in February. Stay tuned and follow UFRGS in our social media. Goodbye.